Let's take a problem which is based on power engineering and which is asked in year 2009. So I am taking a problem get AME 2009. So first of all I will write the problem here. The inlet and outlet condition, the inlet and outlet condition, outlet conditions of steam for an adiabatic of steam for an adiabatic adiabatic steam turbine adiabatic steam turbine RS indicated in RS indicated in the notations RS usually followed. RS usually followed. So now I am drawing the diagram. That is a typical turbine block diagram. Here inlet, I am giving the inlet properties enthalpy 3200 kilojoule per kg, velocity 160 meter per second, Z1 10 meter, pressure that is 3 megapascal. Outlet we are having enthalpy 2600 kilojoule per kg, V2 equals to 100 meter per second, Z2 equals to 6 meter and P2 equals to 70 kilopascal. In that problem, if mass flow rate of steam through the turbine is 20 kilogram per second, the power output, then find the power output of the turbine. That is the first part of the problem. In the second part, assume the above turbine to be a part of simple Rankine cycle. The density of water at the inlet to the pump is 1000 kilogram per meter cube. Neglect kinetic energy and potential energy. Find specific work that is kilojoule per kg supplied to the pump. So in that problem we are interested in power output of the turbine, and in the second part we are interested in the pump work. So now we have to solve this problem. So in the first part, if we see the diagram here, in the first part the inlet and outlet conditions are given and we are interested in power output. So now let's start the solution. I am writing the steady flow energy equation for turbine. So the steady flow energy equation for the turbine will be at inlet enthalpy H1G plus V1 square by 2 plus Q1. I am writing the steady flow energy equation on per unit mass basis. H2 plus Z2Z plus V2 square by 2 plus W. So in the steam turbine process is adiabatic process. So Q will be 0 for adiabatic process. Adiabatic process. So now we are having H1 plus Z1G plus V1 square by 2 equals to H2 plus Z2Z plus V2 square by 2 plus W. H1 is given, that is 3200 kilojoule per kg. So in terms of joule, 3200 multiplied by 10 to the power 3, that will be joule per kg. Plus Z1 is given, that is 10, and G we know 9.81, plus V1 is given, that is 160. So 160 square by 2 equals to H2 again 2600 into 10 to the power 3, that is in joule per kg, plus Z2 is 6, so 6 into 9.81, plus V2 is 100, so 100 square by 2 plus W. So now we can easily calculate the W equals to 600 into 10 to the power 3 plus 39.24 plus 25600 minus 10000 divided by 2. So if we calculate all these things, we will get 607,839.24 into 20 joule per second. So now we can easily convert into megawatt. So in megawatt it will be 12.156 megawatt. So the correct answer for the first part is 12.156 megawatt. Now in the second part we are interested in specific pump work. So we are interested in specific pump work, and suppose it is denoted by WP. So if we know the theory regarding Rankine cycle, so in which we are having two kinds of formula especially for pump work, it may be the difference of enthalpy or it may be VDP. So I am using the second one, that is VDP. So I am using VDP formula for that. So WP equals to V, the reciprocal of that, it will be density, and delta P, so we are having P2 minus P1. P2 minus P1. So in that problem, density is given, that is 1000 kilogram per meter cube. P2 is given, that is 70 kilopascal. So that is 70 kilopascal is given, and P1 is given 3 megapascal. So we have to convert in kilopascal. So P1 will be 3000 kilopascal. So now we can easily calculate WP. 1 upon 1000. P2 is 70 minus 3000. So if we calculate this thing, 70 minus 3000 divided by 1000, so it will come around 2.93. So this one will come around, this work is come around 2.93 kilojoule per kg. So it is coming negative, means that is the work done on the system. So the pump work, that is per unit mass of the steam, will be 2.93 kilojoule per kg. Now let's take another problem which is asked in year 2008. So I am writing the problem which is asked in year 2008. Get AME 2008. I will write the problem for 2008. A thermal power plant, a thermal power plant operates on a regenerative cycle, operates on a regenerative cycle with a single open with a single open feed water heater as shown in figure as shown in figure for the state points shown the specific enthalpies are H1 equals to 2800 kilojoule per kg and H2 is 200 kilojoule per kg. The blade to the feed water heater, the bleed to the feed water heater is 20% of the boiler steam generation rate. Find the specific enthalpy at state 3. So now I will draw the diagram. So by this diagram it will be very easy for understanding the problem. So here I am having a pump. So this one is the pump here, and this pump is feeding water into the boiler. This one is boiler, and from boiler steam is entering into the turbine, and then here it is going into the condenser, here, and from here condensed extraction pump is there, and then again this is entering into the open feed water heater, and the steam is also coming from the turbine, that is stage 1. Here that is stage 2, and this water is leaving from that is stage 3. So now this water will be pumped into the boiler through this pump. So this one is boiler feed pump. So now from diagram it's very clear, and we are having the enthalpy at 1 and 2, and we are interested in 3. Now let's solve this problem. So I am solving this problem, and for this problem, whatever the diagram, the block diagram they shown in the problem, on the basis of that I am drawing the just TS diagram, and on which I will mark the uh, expected states. So TS diagram. So this one is the dome because we are working on Rankine cycle. We are starting from here. From here to here, suppose there is a turbine work, and from this one is the one point where the point two of the steam is extracted. Means the 20% of the steam is extracted from point one as per as problem. So here extraction of, we can select point 2 m of the steam from point 1, and then after that again it is doing the work. So here the remaining steam, that is point 0.8 m, and now this one will enter into the condenser here, and now from condenser is a pump, and we are mentioning this point 2 as far as the problem, and 2 it is now in the feed water heater at point 2. The total water is 0.8 m, and due to this feed water heater, what is happening, 0.2 m of steam is coming, 0.8 m of water is coming here, and then the final water at uh, 3 stage will leave the feed water heater. So now that is the process for the feed water, and after leaving that again it is pumping, and it is pumping into the boiler, and then boiler it is reheating up to this point. So this is a complete diagram for this process, and here I am representing the states only for 1, 2 and 3. So now the energy balance equation for heater I can write. So energy balance for feed water heater, feed water heater. So it's a very straightforward. If you see at 1, the point 2 here, point 2 m of steam is extracting from the turbine at enthalpy 1. So I will write point 0.2 m of steam at enthalpy H1. Now here if you see, it is mixing with 0.8 m of water at enthalpy 2. So it is mixing with 0.8 m of water at enthalpy 2. So now after mixing, if you see this thing, after mixing, the water is leaving at the stage 3 from the feed water heater at enthalpy 3. So I can write equals to mH3. So now if we simplify it, 0.2 H1 plus 0.8 H2 equals to H3. So 0.2 H1 in the problem it is mentioned 2 at 0, 0, plus 0.8 H2 in the problem it is mentioned 200 equals to H3. So 560 plus 160 equals to H3. So H3 in that problem is coming 720 kilojoule per kg. So the correct answer, the enthalpy at the state 3 is 720 kilojoule per kg. Now let's take in another problem which is asked in year 2007. So get MU 2007 problem I am writing here. Which of the following statement, which of the or which of the following statement is correct. The the incorporation of reheater reheater in a steam power plant in a steam power plant P always increase the thermal efficiency, always increase the thermal efficiency, thermal efficiency of plant. Q always increase the dryness fraction of steam, always increase the dryness fraction dryness fraction of steam at condenser inlet at condenser inlet or always increase the mean temperature of heat addition, always increase the mean temperature of heat addition, the mean temperature of heat addition, or S, always increase the specific work output, always increase the specific work output. So these are the four options, and now I will give the options. From them we have to choose the correct one. So the choices for these questions are A, P and S, B, Q and S, C, P, R and S, and D, P, Q, R and S. So I am giving the solution for this problem. So I will write an important fact here, and on the basis of this fact we can easily find out the correct options. So now I will write down the things which is regarding to the reheater. So reheater always increase always increases the dryness fraction of steam at condenser inlet at condenser inlet. It also increases the specific work output. The specific work output. So on the basis of this statement, the correct answer is B, Q and S. Q always increases the dryness fraction of the steam at condenser inlet, and S is always increases the specific work output. So the correct answer is B, Q and S. Now let's take another problem which is asked in year 2005. So I'm writing the problem which is asked in GATE. Amy 2005. So I am writing the problem here first. In the velocity diagram, shown below, u equals to blade velocity, c equals to absolute fluid velocity, and w equals to relative velocity of fluid, and the subscripts and the subscripts 1 and 2 refer to inlet and outlet. Okay. So I am just drawing the diagram here. This one is u1 equals to u2. Here we are having w1. This one is c1. Similarly, we are having c2, absolute velocity, and relative velocity, that is w2. So now the options are A, an impulse turbine, B, a reaction turbine, C, a centrifugal compressor, a centrifugal compressor, or D, an axial flow compressor. So now let's solve this problem. If you are seeing the diagram, so from diagram u1 equals to u2, and if you see the w2 and w1 magnitude with the help of this diagram, we can say w2 is greater than w1. So the relative velocity of fluid at outlet is more than relative velocity of fluid at inlet. So it's in case of reaction turbine. So we can say that it's in the case of reaction turbine. It's a case of reaction turbine. So the correct answer for this problem is B, a reaction turbine. So now let's take another gate problem which is asked in year 2004. So I am writing the problem for gate 2004. The compression ratio of a gas power plant cycle corresponding to maximum work output for the given temperature limits of T mean and T max will be A T max by T mean to the power gamma by 2 gamma minus 1. B, that is T mean by T max to the power gamma by 2 gamma minus 1. C, T max by T mean to the power gamma minus 1 by gamma. And D, T mean by T max to the power gamma minus 1 by gamma. So, as you remember, we have already discussed in Brayton cycle theory the compression ratio corresponding to maximum work done or compression ratio corresponding to maximum efficiency. So, in that problem, we are interested in compression ratio corresponding to maximum work output. So if we see all the options, the correct options will be A according to our theory, T max by T mean to the power gamma by 2 gamma minus 1. So the correct answer for this problem is A. Now let's take another problem which is asked in year 2004. So I am writing the problem for year 2004 here. Consider a steam power plant. Consider a steam power plant power plant using a reheat cycle using a reheat cycle as shown. Steam leaves the steam leaves the boiler and enters the turbine and enters the turbine at 4 megapascal 350 degree centigrade. H3 is given 3095 kilojoule per kg. After expansion in the turbine, in the turbine to 400 kilopascal, H4 equals to 2609 kilojoule per kg. The steam is reheated to the steam is reheated to 350 degrees centigrade. H5 equals to 3170 kilojoule per kg and then expanded to low pressure turbine and then expanded in low pressure turbine to 10 kilopascal. H6 equals to 2165 kilojoule per kg. The specific volume of the specific volume of liquid handled by pump can be assumed to be very small, can be assumed to be very small. So now in that question, find thermal efficiency, thermal efficiency, efficiency of the plant, neglecting pump work, neglecting pump work, pump work. Also find enthalpy, enthalpy at pump discharge, pump discharge, that is H2. So now let's solve the problem. So in that, first of all, I am drawing the block diagram for our clear understanding. This one is boiler, boiler, and from boiler, the steam is entering into the turbine. This one is the turbine here. At point state 3, H3 is given 3095 kilojoule per kg. Now the steam is entering into the boiler from step 4. H4 is given 2609 kilojoule per kg, and now from boiler steam is again coming at step 5 with enthalpy 3170 kilojoule per kg, and now again it is entering into the turbine. This one is turbine, and now from turbine steam is leaving at state 6 with enthalpy 2165 kilojoule per kg, and now this steam is entering into the condenser, and it is leaving at state 1 with enthalpy 29.3 kilojoule per kg, and it is entering into the pump, and through this pump it is entering into the boiler at step 2. So this one is pump. This one is the typical block diagram for this problem, and here we are interested in thermal efficiency neglecting pump work. So now for finding thermal efficiency, let's start with turbine work. So WT turbine work. So if you see, turbine is doing work twice here, from H3 to H4 and then H5 to S6. So for turbine there are two work, it is from H3 to H4 plus H5 to H6. So we can calculate W2 easily. H3 3095, H4 2609 plus H5 3170 minus S6 2165. WT equals to first 3095 minus 2609, so it will come 486 plus 3170 minus 2165, so it will come 1005. So if we add it, then we will get WT equals to 1491 kilojoule per kg. That is WT. And we have to neglect WP. So W net will be WT minus WP. So it will be Wt if we neglect pump work. So Wnet will be 1491 kilojoule per kg. Now let's consider the Q1 heat supply. Heat supply. So heat supply will be Q1. Here we are supplying heat. Here the enthalpy is changing from H4 to H5, and here also from 2 to 3. There is heat addition process from 4 to 5 and 2 to 3. But here we have to neglect the pumper, so heat addition from 1 to 3 and 4 to 5. So heat addition from 1 to 3 and 4 to 5. So H3 minus H1 plus H5 minus H4. So Q1 H3 3095 minus H1 to 29.3 plus H5 3170 minus H4 2609. So Q1 equals to 3095 minus 29.3. So it will come 3065.7 plus 3170 minus 2609. So it will come 561. So if we add these two things, it is 3065.7 plus 561, we will get 3626.7 kilojoule per kg. So now we are having the net work done and we are having the heat supply. Now let's calculate the thermal efficiency. So thermal efficiency equals to eta W net by Q1. So thermal efficiency W net I am having 1491 and Q1 I am having 3626.7. So if you calculate this thing, 1491 divided by 3626.7, so it will come 0.411, or we can say that 41.1%. So the correct answer for thermal efficiency will be 4.411, or we can say that 41.1%. Now we have to calculate the enthalpy at pump discharge. So now for pump work we are having work from 1 to 2. So for pump work we can say the enthalpy change will be H2 minus H1, H2 minus H1. So pump work here we are having the negligible pump work here. So H2, that is the discharge at the pump, will be Wp plus H1. So H2 equals to H1, we know the value of H1, that is 29.3 plus Wp. So the correct answer, H2 will be greater than 29.3 kilojoule per kg. So H2 will be greater than 29.3 kilojoule per kg.